Okay, hello everyone. So this is, this is for section 4.3, but I did want to finish an example because I gave you the definition in class and I didn't do an example. So I just want to do an example of showing that a function is increasing. So here we have the function, it's a piecewise function, f of x equals x squared if x is less than or equal to 2, and 6 minus x if x is greater than 2. Okay, and so the question is show that f restricted to the closed interval 0, 2 is increasing. Okay, so something in terms of before we do the proof, we note that f restricted to 0, 2, so we're just looking at the closed interval 0, 2 is just the function x squared, right? So f restricted to 0, 2 is the function x squared. So we need to show that f of x, which equals x squared, is increasing on 0, 2. Okay. And actually, so let's pause. Okay. So this proof is actually, let me go back. This proof is actually in your book. And, okay, so now let's start the proof. Okay, so first we let x, y belong to the interval 0, 2 and the closed interval 0, 2. So suppose x is less than y. Okay, so again, I'm just using the definition of increasing, right? So we need to show, so in our show part, f of x is less than f of y. So that means x squared is less than y squared. Okay. Well, since x is greater than or equal to 0 and x is less than y, then we can say x squared is less than or equal to x times y. Right? So we just multiply both sides by x of this inequality, but since x could technically be 0, we have to make it less than or equal to x times y, right? Just in case x is 0. Okay? And then, okay, also, since x is less than y and y is greater than 0, okay, then we have x times y is less than y squared, okay? So we sort of look at this inequality from both the perspective of x and the perspective of y, okay? And that's how we get that. And so, hence, by putting those together, we can say x squared is less than or equal to xy, which is less than y squared. Okay. And so we just showed that x squared is less than y squared. We can do our therefore. Therefore, f restricted to the closed interval 0, 2 is increasing. Okay. So pretty straightforward. Again, the proofs we get into are not necessarily long, but you really have to make sure you understand the definition correctly. Okay, so now that's the end of section 4.2, and moving on to section 4.3. Okay, there are the homework problems for section 4.3. So these are the problems that you'll be working on in class. So number 1A, and then F through H, and then number 2A, and then 3A and B, and then 4, and then 5 through 6. So those are the problems for section 4.3. Okay, And so a fact, I don't know if I stated this already in class, but if not, a nice fact we have is, remember, when we're mapping a function from A to B, A is the domain and B is the codomain, right? B is the codomain. And so the range are all your values that A maps to, and it doesn't necessarily have to be the entire codomain, right? But whatever set it is, we call that the range. And so something that should be obvious is that the range of F is a subset of the codomain, right? Okay. So now we're looking at onto. If F is onto B, and we can say F maps from A to B. Okay. So if F is onto B, that means your range of F actually equals B. Okay. So that's what that means. Okay. So in terms of understanding the proof structure of onto, or proving that something is onto, we have that. So we say if F, and when I do this, I want to be careful, because I think for those of you on the quiz, with the equivalence, the last quiz, part 1 that we had, where you had to prove it was an equivalence relation, I think you took those variables as they were and felt that you couldn't move them. But remember, these are just sort of, you could change up your variables, okay? It doesn't have to be set in stone. So in general, what we're saying, whatever your domain is, so F maps from A to B. These are just general, so it doesn't have to map. It could be the domain could represent a 2x2 matrix. It could represent Z4. It could be something different, okay? But this is sort of overview. Whatever your function is, that maps from A to B, and B could be anything as well, okay? So F goes from A to B, so F is on to B. Proof-wise means for every Y in B, so everything in your codomain, there exists an X in A such that F of X equals Y. Okay, so and hopefully that makes sense. I'm saying whatever element is in your codomain, whatever element is in, so whatever element is in B, for any element you choose in B, there exists a A. And remember, in terms of quantifiers, that X will depend on that Y in most cases, right? And certainly in a lot of cases. There could be some cases where it's just a general term, and we'll talk about that. But in general, that X is going to depend on that Y, such that F of X is equal to Y. Okay, so we're going to look at this one proof, and then I'll probably stop this video and start another one. There's just going to be 2 videos for this section. It's not an extensive section. In your book, they actually have it's just a lot of examples in there, so make sure you read the book as well. So example 1, we're going to prove that F going from R to R, the reals, where F of X equals X plus 2 is onto R. Okay. For onto functions, for the most part, I would say, I don't like to say for every case, because there could always be an exception to the rule. But for most cases, you're going to do some side work first, because if you remember, so let's do some, I don't want to use this marker. So let's do some side work. Because again, in this case, so in this instance, we're saying for every Y in the reals, there exists an X in the reals such that F of X equals Y. And remember, whenever in our proof we see there exists, that means we have to show what it is, right? We have to show what it is. For all, it's just in general, but for there exists, we have to show it. So first, let's find out what that X is. So that's why we have to do some side work. So we have F of X equals to Y, right? Well, we know what F of X is, so we just say X plus 2 equals Y, and then we solve for X. Okay, so that's going to be X equals Y minus 2. And there we have our X value, okay? So now we can start our proof. Let me see if I can get it all on this page. This is not going to be too long. Let's see. Okay, so the first thing we do in our proof again, this right here is the proof structure. So the first line should be what? Let y belong to the reals, right? Because that for all means just keep it in general. So let y belong to the reals and let x belongs to the reals such that x equals y minus 2. Okay, because we found out, right? We found that x. So f of x equals f of, now we substitute in what we found for x, y minus 2, and that equals, according to this function right here, is going to be y minus 2 plus 2, which equals y. Okay? Therefore, we just proved it. F is onto R. Okay, so I'll stop this video now and start the next one.